And I think it was this one. Oh, I got it right here. Okay, the way that this distribution works is, let me draw this here. Oops, my goodness, that was pretty impressive. Okay, let me put this aside for a second. See if I can't copy this out of here. That's going to be tough. Okay, tell you what I'm going to do. I am going to grab this thing. Okay, let me close this off. That document, by the way, is available to you when you want, if you want to see it. I'm gonna, okay, let's copy. Okay, I'm gonna open this up. Okay, here's our chi-square distribution. Okay, it always has roughly this shape, just like a normal distribution normally has the shape that it comes with, that bell-shaped curve. Okay, and what this shape represents, I just want to get rid of this stuff over here so it doesn't distract us. What this shape represents, it represents the probability, right? This is the probability of a certain outcome, right? And that probability, our chi-square value, right? Our chi-square value, the smallest it can be is 0. The chi-square value can't be any smaller than 0 ever, because that would indicate the numbers are exactly the same in your observed values and your expected values, right? You'd get a chi-square value of 0. The minute any of these numbers are different than a number in the corresponding table, then you're going to wind up squaring things, and it's always going to be a positive number. So chi-square is always going to be a positive number, right? Now, if you get a situation where you're dealing with, let's say, I'm looking at male and female is my exposure, okay, and I'm looking at, let's see, my outcome is, let me think of something that's not going to, okay, is going to be, let's see, ability to let me come up with something better than this. Let's see. Left-handers, lefties, and righties, and the outcome is going to be HIV status. Now, I got no reason to believe that there's any association between right-handed and left-handedness and HIV status. So my expectation is that my observed values and my expected values are going to be the same thing. And I'm going to wind up with a chi-square of 0. The problem is that even if this is true, even if H null, right, that there's no association between left-handedness or an HIV status, even if there's no association, the likelihood that I would get, let's say, that I would get exactly the same outcome when I actually sample that population is very low. Okay, I would probably get a chi-square value with a small number, maybe 0.5, maybe 1, maybe even 2, right? Well, that's what this curve represents. The height of this curve represents the probability of my getting that outcome for chi-square when there's no difference between the two groups, when there's no association between the exposure and the outcome. And if you look here carefully, the probability of getting 0 is pretty low. Actually, the probability of getting a small chi-square, I don't know, like maybe something like 0.5, that's pretty likely. You would expect a small difference between the two. not a perfect observed and expected outcome. But now, as chi-square gets bigger and bigger, it becomes more and more unusual, right? So now, for me to to cover 100% of the chances of chi-square of values of chi-square that you could get when there's no association, well, sometimes you might get something extreme. Extreme. Maybe you get a chi-square as high as high as 5, even, right? The likelihood of that occurring is very small. So now I have to make a decision. What is different enough for me to say that there's no association? Okay, so now if I wanted to be 100% sure that there's no association, I might have to be all the way out here at 19 or something like that to have zero. In other words, as we get further and further, the area here gets tinier and tinier. But this is asymptotic. It never really hits zero. It could get ridiculously small, but it's not zero, right? So I could go away. So I have to make a decision. At what point am I willing to say that the difference is not due to chance? As this all represents the size of chi-square due to chance, even when there's no association. How far out here do I have to be willing to be before I can say that the difference is real and reject my null hypothesis that there's no association? Well, by convention, we usually say that we're willing to accept 5% chance of being wrong. So that means in our case, that represented a chi-square value of 3.841, right? That meant that there's only 5% chance that with when you have 1 degree of freedom, there's only 1% chance that you would be on this curve in an area, right, all the way down here at the right end of this curve, but still be in a situation where it could be part of an association which doesn't exist, that there's no association. So even though you got bigger than 3.84, there's still a chance that it could be part of this distribution. But it's so unlikely that you're willing to ignore that. It's less than 5% chance of that happening. So now the bigger the chi-square value is, right, the further out you are here. So when you're using the table, all we really care about is the critical value that we need for this area that's left to be 5%. When we're using a computer, well, when we calculated our chi-square value, I think it was 4.1 or something like that, right? When we calculated our chi-square value, we knew it was to the right of or past 3.84, so we can reject our null hypothesis. We knew that based on the critical value in the table, right? However, when we use software, it'll actually tell you what the area left to the right of that is. So not only will we know it's less than 0.05 because it's bigger than the critical value, which is set at the point where it's 5% for that particular number of degrees of freedom, but we'll also know exactly what that p-value is. That p-value, since it's past the critical value, that area to the right of that number, 4.1, is always going to be less than 0.05. It might be 0.13, or 0.01, excuse me, 0.013, right? Less than 0.05. But we'll actually know what that p-value is. So when we use software, normally what we're doing is looking at the chi-square value, but we're not necessarily checking the table. We're just looking past that to what the significance or p-value is and making sure that it's less than 0.05. In this case, whether we did it by hand or we did it using the software, in this case, both cases, we're going to reject the null hypothesis. Okay, we're going to give it a try using software to see how that works, how well that works. Okay, and I'm going to tie this in to the idea of what we're going to do with our projects. In other words, this gives you another dimension that you can look at in terms of projects. So let's move on to some actual data. You got tons of stuff I put up on Blackboard that I'm not going to use right here, including some, pictures of the formulas and so on and so forth. Oh, I wanted to mention one other thing, and that is that we typically we get concerned if any of these cells have a value less than 5. That's one issue. And the other thing that we get concerned about is that, there's a problem with this calculation. It's really more of an estimate than anything else. There is something when you have relatively small numbers in here, very frequently you do something called a Yates correction or a continuity correction. And what you do there is that before you square this number, you actually subtract zero point 0.5 from that number. Okay? In other words, you find your observed value minus your expected value. You subtract zero point 0.5 and then you square it over and then put it over your expected value. Actually, I think I got that wrong. Yates correction. Is it after you square it or before you square it? I'll have to look it up. However, we make a correction by subtracting zero point 0.5 from each one of these calculations. Now, what does that do? That makes the number that we calculate here a smaller number. It makes this a more conservative test. For our purposes, we'll leave that up to SPSS to do. I'm not going to ask you. So, well, since we don't have another test, I won't be asking you anyway. But if we had another test, I probably would let you just use the formulas that we've used here without having to worry about that continuity correction or that Yates correction. Okay. I threw a little thing. I know that that's kind of a curveball, and at this stage, it could be a little confusing to you. But what I'm basically saying is don't worry about the Yates correction because we're not doing it by hand, and the software will take care of it by itself. Okay, so we're going to move on and actually do this using SPSS. And one of the ways we're going to do, I'm going to open up an SPSS file called stenosis and smoking. It's on Blackboard. If you want to, you can, if you've downloaded it, you can open it as well, but you don't have to. You can actually if you want, you can relax and watch me doing it. Okay, and of course, my version is starting to wear out, so I'm going to have to cross my fingers and hope it opens up. Oh, yep, gave me the warning back there. I know that. I don't know why it does that. That must be double clicking, eh? Okay. Oh, okay. It's not bothering me with the warning anymore for some reason. For whatever reason. Okay, so let's take a look at this data. This data has 3 variables in it. It's got smoking status, no and yes. It's got disease status. In this case, it's arterial stenosis, or in other words, narrowing of the arteries, right? Coronary arteries. And it's got gender in it too, for that matter. Maybe we're not interested in gender right now. We're interested in whether being a smoker increases your risk, is associated with your risk for stenosis. Okay, so we want to analyze this data. I can click up here in the view, and I can change. So you can see that this is ones and twos, and this is ones and twos here, the real data. I'm going to go turn it back on so that we can see the values again. Okay, and that's actually defined back here in our variable view. Okay, you'll notice that for smoking, right? His smoking, the label is smoking status. That's what's going to wind up on all our charts, and the values that it can take. It's a nominal or categorical variable. It can take a couple of values. 1 means yes, they're a smoker. 2 means no, they're not a smoker. Right? We wouldn't take an average of that. It's not numerical data. It's nominal data. Okay, and the disease outcome is either yes, they have stenosis, or no, they don't have stenosis. Okay, the variable name is disease, but the actual label that's going to show up is presence of aortic stenosis. Okay, so I'm going to go back to data view again just so that I can see this. Okay, I'm going to ignore the 3rd variable for now. We're only going to work with these 2 variables. So I got a lot of people here. So I need to organize this data. I have 215 subjects in this study, randomly selected subjects, right? So I need to organize this data. So I'm going to go up to Analyze. Now I know that I'm going to since it's categorical data and there's an exposure and an outcome, I'm going to organize this into a contingency table, right? Just as we were doing it now. So I'm going to go click down here And I'm going to go descriptive. And I notice that there's something under descriptive statistics called crosstabs. Crosstabs is another way of saying contingency table, right? Cross-tabulation. So I'm going to click on that. I'm going to try and click on it, right? And notice it comes up with rows and columns. Now I'm going to put the exposure in the rows. Which one's the exposure? Anyone want to hazard a guess which one's the exposure? Yes? Someone? Yes? Right? Exposure is, which one is the exposure here? Smoking, right? Smoking. Let's put smoking into the rows, put the outcome, aortic stenosis, into the columns. Okay, so now I got a bunch of options that I have here. I'm going to click on this first one, statistics. Oh, well, look, chi-square, that's what we're just working with. And look, risk, we were talking about risk also. I'm going to ignore that for the moment. I'm not going to check any of them off. I'm not going to calculate that. I'm instead going to go to cells, and I'm going to click on this. Now, you don't have to do it the way I'm doing it. I'm doing it this way to demonstrate this to you. Observed, the only thing that's checked off right now in cell display is observed values. It's going to organize all of these subjects into our observed values. I'm going to click continue, and I'm going to click OK. Let's see what comes up with my output on SPSS. Well, take a look at what happens here. I have a table, and on the top is smoking. Yes, smokers are in the top row. Non-smokers are in the bottom row. Presence of aortic stenosis. Yes and no. So we had 215 people in the study. Of those 215 people, let's see, 117 did not have aortic stenosis. 98 people did have aortic stenosis. And we found, let's see, among the people that are smokers, 54 had aortic stenosis. And among the people that were not smokers, 44 had aortic stenosis. It's less. But there's more people here. It's kind of hard to judge, right, just by looking at those numbers. So we want to calculate our risks. Okay, so how do we calculate our relative risks? Well, I need to 54 out of 94 people is my risk for smokers, and 44 out of 121 is my risk for non-smokers. Well, let me see if I can't get SPSS to do that for me. I'm going to go back to Analyze, Descriptive Statistics, Crosstabs again. Except this time when I go into cells, I'm going to say, instead of cells, I'm going to go into statistics. I'm going to say, I'm going to stay there. I'm going to say calculate the percentages by rows. And I click continue. And say OK. And look what it did for me this time. It found that my smoking status, yes, 54 out of 94 people, 57% of smokers in this study had aortic stenosis, but only 36% of smokers, non-smokers, had aortic stenosis. So I could say that 54 over 94 is 57%, 44 over 121 is 36%. My relative risk is 57 over 36. Or another way of putting that, 54 divided by 94 divided by 44 divided by 121, just as we calculated it before. So my relative risk looks to be roughly, I'm going to guess, about 1.6, 1.7, would you say? If I divided 57 by 36, 57% by 36, about 1.6, right? So I am going to actually ask SPSS to do some more calculations for me. Okay, now that's nice if I want to calculate my odds ratio. Somebody tell me what numbers, what's my odds of aortic stenosis if I'm a smoker? What would my odds be? You can just tell me the two numbers you got to divide by each other. Just for smoking status, yes. What are my odds going to be? Somebody tell me what our odds are. Remember the A, B, C, D, A over B, C over D odds? Somebody calculate my odds so I have some reassurance that you guys are catching some of this. 54 over 40, right? A over B, right? There are 54 people out of 94, 54 people had stenosis, 40 didn't. So the odds are 54 to 40, or 54 over 40. The odds of not having stenosis, of if you're not a smoker, are 44 over 70, 77. So 54 over 40 is about 1.1 and a quarter, let's say. And 44 over 77 is about 2/3. So 1 1/4 divided by 0.6. I'm thinking that's somewhere around 2-ish is my odds ratio. Just like I had about a 1.6 or something like that for my relative risk, my odds ratio looks like it's going to be around that too, or maybe a little bit higher, right? So now I'm really going to go all out. I'm going to go to Analyze, Descriptive Statistics, Crosstabs. I'm going to tell SPSS to calculate a whole bunch of stuff for me. I'm going to go into cells. I'm going to tell it to calculate my expected values. Continue and say, okay. See what I get this time. Well, now, not only do I have my percentages, but it also calculates, well, if you're overall frequent, if there's no difference between being exposed to smoke, being a smoker and being a non-smoker, well, gee, I would have expected in this cell to have 42 people and 51 people, and in this cell I would have expected to have 55 and 65 in these two cells. These are my expected values if there were no difference between smokers and non-smokers. So instead of making a separate table, it puts it all into one table. My observed values or counts are 54 and 40. My expected values for those same cells are 42 and 51. My observed 44 and 77. My expected 55 and 65. And you guys remember what we did for calculating a chi-square, right? From this table we can calculate our odds ratio, our relative risk, and now we can calculate our chi-square. Observe 54 minus 42.8, but that's calculated, so it may not be a whole number. 54 minus 42.8, right, squared, divided by my expected value, 42.8. That'll give me a number. And then the next box and the next box, and add them all together will give me my chi-square value. Okay, I don't need to do that myself. I can ask SPSS to do that. Analyze, descriptive statistics, crosstabs, and I'm only doing this step by step to show you have a lot of options here. Please calculate my chi-square value and calculate my risks, my relative risk, my odds ratio, and so on and so forth. And I'm going to click OK. And then I'm going to click OK again. Okay, so now it's going to give me that table back, but now it's going to give me a couple of new tables, right? So it's 1 degree of freedom, just as we would have expected. And our Pearson's chi-square value is, and the calculation that we did for chi-square is called Pearson's chi-square, by the way. Pearson's chi-square value is 9.48. Okay, now just looking at that number and knowing for 1 degree of freedom that the critical value for chi-square is 3.4, can you reject your null hypothesis that there's no association between smoking and an aortic stenosis? Can we reject our null hypothesis? Somebody? Nicole? Jillian? Jennifer? Can we reject our null hypothesis if we get a chi-square that big? Yeah, we all agree we can, right? Not only that, but it actually gives me, now ignore this two-sided, because it only puts that in there to make sure that you don't bother to double the number. Okay, it's really a one-sided test. Okay, my probability of getting that big a chi-square value, if there's no association between smoking and stenosis, is only 0.2%. It's well below 0.05. So it's nice to be able to get the chi-square and compare that to the critical chi-square value on the table. But SPSS actually gives us a probability of being wrong if we reject the null hypothesis. And we could use either the chi-square value or we could use the p-value, the significance, either one of them, and compare that to 0.05. Both of them give us a justification for rejecting the null hypothesis. let's take a look at our relative risk and our odds ratio, because SPSS calculates that for us as well. See what we got here. Our relative risk, let's see, our odds ratio for smoking status, yes versus no, is 2.3. The odds are 2.3 times as likely for smokers as opposed for non-smokers, with a 95% confidence interval of 1.3 to 4.1. What's the significant number that's missing between the lower range and the upper range in the 95% confidence interval? What's not in that range that's important to us? Somebody tell me. One, right? We can say with 95% certainty that the odds ratio is different than one, that there really is an association. Now, how about for now this line here is our relative risk. If you look up here, remember 57% divided by 36%. I said that looks like about 1.6. That's our relative risk. Okay, it gives it kind of a funny name, right, for cohort presence of aortic stenosis, right? But that's our relative risk. Similarly, our relative risk excludes the number one. So we know that we can reject the null hypothesis because our Pearson's chi-square value was bigger than our critical value, because the significance or p-value for that analysis was less than 0.05, because our odds ratio for smoking status versus aortic stenosis excludes the number one, and because our relative risk confidence interval excludes the number one. Those four things give us justification for rejecting the null hypothesis. So now, how does this affect all of us? Well, one of the things that I put onto Blackboard that you might be interested in taking a very close look at is a study that's done annually by the New York City Department of Health, a health survey of all New Yorkers. And I have a copy of it here, I believe. Oh, I have a copy of it here in data sets. And the most recent one is for the year that's been accumulated is for the year 2010. You have two files. You have one is a code book. One is basically a description of the questions that they asked, the choices that they were given, and so on and so forth. So, for instance, let's see what we got here. For instance, diabetes. Yes, one yes, two no. And then they also had some other things they could put in that would be basically non-answers or didn't know. Okay, so we have diabetes has two values, has the value 1 for yes and the value 2 for no. That might be an outcome. Well, what can we analyze? Well, there's many other variables here that they asked about. Mood, mental health treatment, whether or not you had a physician, a private physician, whether or not you walk much during what your activity level is, and so on and so forth. So we can take categorical variables from this study, and I'm going to open up the data file itself. Okay, here's the data file itself, and I'm going to choose a couple of these variables. I'm going to dinker around a little bit here, see if I can't come up with something interesting. Crosstabs? Well, now I got to choose which variables that I want to use here. So let me see if I can't find the one for diabetes. See, look at all these variables we have here. Strata. Let me see if I can't find diabetes again. Have you ever been told by a doctor or nurse? Let me hover over this, see if I can't get it to show that you have had asthma. Okay, so let's put that into the columns for outcome. Let's see what we might want to compare that to. Smoking status. Okay, let's put smoking status into rows. Now, I haven't even looked at this data really. They're both categorical or nominal data. I can see by the symbol that's in front of them. I'm not sure what the various values are. So I'm going to go into cells, and I'm going to ask SPSS to just show me the observed values for now. I'm going to click OK. And look what it did. It organized it for me. Let's see. Smoking status 1 was, let's see, 658, 446. So it looks like, I'm going to go back there and ask it to give me the percentages by rows. Crosstabs. And give me the percentages by rows. That'll help me figure out what's going on here a little bit better. Okay. So let's see. Smoking status. 12.14% of people that have been told that they have asthma by a doctor are smokers. And let's see, the variable 2 was actually is 3. You know what? This might be like smoke a little, smoke a lot, or not smoke at all. That's what this could actually represent. How would we know what this is? Well, if this data had been coded with the values for 1, 2, and 3, we would have seen that here, what those represented. But my guess is it represents the amount of smoking. And one might be smokes more than a certain amount. One might be smoked previously smoked, and the third one might be never smoked or something like that. I'm speculating. And this one might represent have been told that you have asthma. In fact, given the numbers, I'd say that's almost definitely what it says. Okay, in the past year, and 2 means you haven't been told that you have asthma. Now, our null hypothesis is that there's no association between smoking status and having been told by a doctor in the past year that you have asthma. I don't know what the outcome is going to be here. It could be that asthma makes it more. Smoking makes it more likely that you would have asthma. It could also be that if you have asthma, you're not likely to be a smoker. So I don't know if the association is going to be a positive thing or a negative thing. I'm going to start out with the assumption and null hypothesis. There's no association between smoking status and whether or not you've been told you have asthma in the past year. So there's a number of ways that we can evaluate that: the relative risk, the odds ratio, so on and so forth. Relative risk and odds ratio we're going to have an issue with. I'll show you. Let's see. Let's see. Descriptive statistics. Crosstabs. I'm going to check off in my statistics chi-square value and risk, and I'm going to go ahead and going to run that. Okay, so let's see what we got here. Okay, risk estimate. Remember, that's where our relative risk odds ratio were? It can't do that because I have 3 levels of exposure. It can only do that for 2 levels of exposure. Exposure or no exposure, or low exposure, high exposure. So I would need to reformat this data. However, chi-square does work for me. It's 2 degrees of freedom because it's 3 rows by 2 columns. And the chi-square value is pretty big. And in fact, I have the same level of confidence that I can reject the null hypothesis. So our null hypothesis is there's no association between smoking status and whether or not you've been told by a doctor that you have asthma. Okay, so my alternative hypothesis is that there is an association. So if my p-value is lower, significance is less than 0.05, I fail to reject my null hypothesis. But my chi-square value is very large. My p-value is less than 0.05, so I do reject my null hypothesis, and my conclusion is that I accept my alternative hypothesis that I can say that there's an association between smoking in this population and having been told that you have asthma by a doctor. Now, what does that mean? Does that mean you have to do this particular study? No, you have many, many, many options here. And we can actually, if you wanted to work with relative risk, for instance, we could go back. Let's go back into our description of this data and look for smoking status. As I thought, never, current, or former are our 3 levels. Maybe I want to eliminate never. So what I would do there is I would only look for the values 2 and 3. So I could reformat this data to remove the values 1 so that we're not looking at 3 rows. We're only looking at current or actually, we could combine never and former into people that don't smoke currently, or we could combine current and former together into smokers and compare them to never. We combine all the twos and threes, turn them into twos, right? So, and we would do that using this transform variable. Now let me see. What was that? That was smoker, right? Okay, question 6-1, smoker, and I want to combine 2 and 3. Let's see. Uh, and I can help you out with this, but I need you to start to look at these data sets that I've put up. And I'm going to kind of like, try and encourage you guys to have no more than 2 people picking the same data set out. So the sooner you kind of like settle on what you might be interested in evaluating, I put a whole bunch of data sets up, including this enormous one. Okay, so let's see if I can't find these. Let's see, smoking status. Where is my smoking status? Let's see. Up smoke. Is that it? Let's look at the variable view. Smoke. Let's look at the values. Oh, there's no values that are given here. Okay, so I got to put values in. Okay, so I forget what they were. One was current. We'll have to actually build this. I'll help you build this also. I forget what the numbers were. One was current. Maybe 2 was. I think 1 was never actually. Two was current, and 3 was former. Okay, so now when I go to my data view and my analysis, you'll see that you can see, and 4 was, I don't remember what 4 was. It might have been a different smoking status too. Well, we can worry about that later on. So if I want, I can create a new variable, recode into a new variable. Okay, and I can say that I'm going to take my smoking status. But that was 6.1. Wonder if that I can find it this way. Was it 6.1? Let me see if I can't find this again. Smoke 66. After mood. Recode into different variables. Here we go, smoking status. I'm going to input my smoking status. I'm going to turn it into a new variable. I'm going to call smoke 2 values. Okay, and I am going to say that, for instance, if the old value is a 1, the new value is going to be a 1 also. That's, I think, never smoked or something like that. And if the new value is a 2, the old value is a 2, the new value is going to be 2. And if the new value is a 3, old value is a 3, the new value is going to be a 2. So now, instead of having 3 variables when I do this, okay. Okay, and I'm going to change, say okay. It executed it. So now if I got the right variables, okay, columns, okay, this time my exposure is going to be this variable in my rows, and my outcome is going to be my, let's see if I can't find the asthma again. Have you ever told bipolar smoking status? Oh, I think I might have got the wrong one there. There's a number of smoking status ones. I might have worked with this wrong variable. Uh, Boy, without looking at the chart, it's kind of hard for me to find this stuff right now. I'm going to put smoking status and likelihood that you're being insured or uninsured. So I'm going to put that in there just so I don't have to play around looking for this stuff. And risk, and let's see if I got it down to 2 variables now, and if it gives me my relative risk. See, well, this time it actually calculated the relative risk because it was indeed a 2 by 2 table. The smoking status was 1 and 2, not 1, 2, and 3. Right? I combined the non-smokers and the former smokers. Excuse me, I combined the current smokers and former smokers together, and the non-smokers were a separate group. And so I only had 2 rows instead of 3. So now it's 1 degree of freedom instead of 2. I still get a satisfactory chi-square, but this time at least I can look at my odds ratio and my relative risk and so on and so forth and see if they help me out as well. In this case, I didn't bother to really go back and check it very carefully, but you guys get the idea. Okay, so now this is really different than what we've done before. And I would be surprised if you really got a handle on it from this first look. But I'm going to ask anyway, because I'm a glutton for punishment. On a scale of 0 to 10, how understandable is this to you? Okay, 0 is completely lost, and 10 is, it's mostly math, mostly just simple math and just looking stuff up on tables or getting the computer to do it. Oh my goodness. Okay, we got a wide range here. Okay, all right. Okay, good. I'm pleased. We have some people that have some issues with it. I can understand that because it's really different from what we were doing before. I'm going to post a very simple homework, which I'm going to take the New York City health data, and I'm going to pull 2 variables out of it, and I'm going to ask you to use SPSS to give me the calculate chi-square value, relative risk, odds ratio. Tell me what the null and alternative hypothesis would be, and so on and so forth. It's going to be a very simple problem. Won't take you long to do. The real key here is that once you learn how to do this, if you decide you want to work with data that is categorical rather than numerical, now you have an option on how to do that analysis. Okay, I'm also going to, also while we're at it, I might also mention that when we're looking at categorical variables instead of numerical variables, well, we're not looking at histograms anymore, are we? Instead, we're looking at, for instance, we're looking at, let me go in here, we're looking at bar graphs, right? We're looking at just simple counts. Okay, and I'm going to see if I can't get my smokers again. Okay, so if we want to display some graphics to get an idea of what these distributions are like in this data, let's see. Are you currently, what is this? Taking meds for high blood pressure. Okay, let's see. Okay, category axis. Let me just see what this looks like. Okay, so this gives you an idea of what the count is among the people that they surveyed. They got about 200 people that are taking meds for high blood pressure, and they got about 2,400 people that aren't taking meds for high blood pressure. Must be a different crowd than I hang around with, because a lot of people I know are taking meds for high blood pressure, but I guess that's, older set of people. Now, let me answer a couple of questions. If you do have a categorical variable comparison of our pressure, so we include all the 2x2s that SPS produces. Yeah, I would. I would include those 2x2 tables. And I would also maybe include some graphics so you could see what the counts were for the number of people that were HIV positive in your study or that were smokers in your study, and so on and so forth. Just like I would include box plots if you're using numerical variables, box plots, so on and so forth. Now, the one thing you haven't seen so far is something that we're going to be looking at next week, and that's correlation and regression. Okay, what if you wanted to compare two sets of numerical variables? For instance, what if you wanted to know whether there was an association between your cumulative average graduating hunter and your salary for your first job after you get your degree? One
And
is a numerical variable, the other is a
you
numerical
okay?
variable. So we can't compare
No.
means, right?
You
Because
need
they're
an
not
umbrella?
related. Well, for that, we're
For
going to
one
use
either.
correlation. And let
I'll
me see
just
if
get
I
in the
have a
shower.
quick
You'll feel
example of
better.
that. Okay, I'm going to take,
Oh,
let's see, I'm going to take violent crime statistics. Okay, so let's see. This is the poverty rate in certain communities, and this is the murder rate. Okay, let's see, is there an association between poverty rate and murder rate? Well, gee, I can't do an average with this. I could get an average murder rate, average poverty rate. It won't tell me where. I want to see if there's an association between these two. The way I would do it with two numerical variables is called correlation or regression. And I'm just going to show you quickly what it might look like for correlation. First thing I might do is take a chart and just do a quick scatter dot chart. In other words, for Alabama, see how the murder rate and poverty rate, how they compare with each other. So I'm going to say simple scatter plot. And I'm going to say in the x-axis, I'm going to put the murder rate. Excuse me. In the y-axis, I'm going to put the murder rate. That's the height. And in the x-axis, I'm going to put the poverty rate. And I'm going to click OK. It's going to make a chart for me. And that chart is going to represent each of the different states, their poverty rate and their murder rates. And it looks like that as the poverty rate goes up, the murder rate goes up also. I have an outlier here, don't I? Right? And that must have been during this period of time that there was one particular city that or state or city that had an issue with it. And if you go through this, you'll actually see that the one that had such a high murder rate, I think, was actually D.C. And this was probably over a short period of time. Let's see if I can't find it. Well, it's going to be the murder rate's going to be 50, so we're close to it. So I should be able to should pop out right here. It is District of Columbia. I'm gonna delete that. I'm going to delete that one and do this again. I'm about to finish, so try not to fall asleep while I just do this one last thing. Okay, so now this is going to be a little bit more dramatic here. Okay, and you can see kind of as one goes up, as poverty rate goes up, murder rate goes up also. Okay, there's an association between them. How do I demonstrate whether that's a statistically significant association? And in fact, we do have tools for doing that. And we call it correlation. In this case, it's called bivariate correlation, for two variables. One variable is poverty, one numerical variable is poverty, the other numerical variable is the murder rate. And we can actually do a calculation. This guy Pearson came up again, didn't he? Okay, and I'm going to put I'm going to put murder rate and poverty in here, and I'm going to do a calculation. And it gives me an output. It gives me a significance. That tells me that I can be have less than 5% chance of being wrong when I reject the idea that there's no correlation at all. And it gives me another number, which gives me how predictable that correlation is, how good a correlation is, how good a predictor that is. We're going to learn about that next week, but we're going to learn about that on Wednesday in class. Okay, I'm going to bring some one of those posters, one of the poster boards we're going to use, so you know how much space you have, what it's going to look like. You're actually going to print out of the 8.5 by 11 paper and paste up your various sections onto the poster board. You'll have 15, 20 minutes to do that before we actually go around evaluating them and so on and so forth. So you'll prep your stuff. I'll give you lots more information about the size of the poster board, so you know the exact dimensions, so you can be a little bit better prepared for it. And maybe even I can come up with an example of what it might look like. And if you're in there on Friday, I can even rip a sheet off so you can see the exact size. Take it with you. So at any rate, but we're going to be looking at correlation. But now you have a tool in addition to all your other tools. Your tools for working with categorical and numerical variables, in other words, your t-test and so on and so forth. Categorical and categorical variables, and now numerical and numerical variables. So there's practically nothing that you can't do something with. This part you're going to learn about on Wednesday, though. Okay, so